at point Q, as shown, with 120 pounds of force, whatever, in 40, and that's basically the length of it, okay? 120 pounds is the magnitude, how long it is. In the direction that this is 40 degrees, but it's going down there like that, okay? Okay, what is the input moment M12, or what's this moment imparted on link 2, necessary to keep the entire mechanism in static equilibrium? And remember, I can't emphasize more that this whole graphical approach, this whole section, everything in this lecture so far is based on static equilibrium. Okay, so if the question is asking what is the moment on link 2 given that force P that causes a constant velocity or something, that you wouldn't be able to use the graphical approach. It's just if this is fighting against that force so that it's static, it's not moving over time, there's no velocities, there's no accelerations, now you can use this approach, okay? And you have to assume the figure is drawn to scale, okay? Because it's a graphical approach. You're going to be getting out your ruler and you're going to be measuring the lengths and directions of these vectors, okay? Okay, so let's solve this. So let's use our logic to deduce, basically get back from what they've given us to what M12 is. Okay, so we first recognize that smooth pin joints can only impart forces, not moments. Okay, so you already know that. So if we pull out link 3, we know certainly there's no one ever imparted a moment on there, and this force P is not imparted on 3. And so the only forces that can be imparted on link 3 would be imparted at point A and B, right? And so that already should tell you, now, you know, sure, at A there could be an X component and a Y component, and at B there can be an X component and a Y component. But all summed together, there's just 2 forces acting on this member, this link. And they are going to be at A and B. And so you say, okay, well, one thing we know about this mechanism is 2-force member, which means whatever those forces are, their lines of action better go through A and B, right? It better go through A and B. And whatever their magnitude and sense are, they've got to be equal and opposite. Now you could deduce, if this is static equilibrium, if this force is pushing down like that, this moment better be pushing like that, and guess what? This is going to be in compression, so you can know their direction, they're equal and opposite. You know, this equals that in length, and they're in different directions. But what you don't know is what the magnitude of these are. You just know they act at A and B. It's a 2-force member. They're going to act along the line that connects A and B, and they're going to be equal and opposite, and they're going to be pointing in that direction. You don't know their length. You don't know their magnitude yet. Okay, so we need to find that. Well, to find that, let's look at what we know about link 4. Okay, link 4 is a 3-force member. Okay, because right, this joint here at B can only impart a force. It can't impart a moment at B, and this at O4 it can only impart a force. It can't do a moment. Okay, so there, and of course at Q we already have this force P. So we have a force at B, O4, and Q, and that's the only loads on that. And so since there's only 3 of them, you know it's a 3-force member. Okay, and you already know the magnitude and direction of this one. That's given to you, right, and where it's acting. And do you know the sense of the force acting at B? Well, sure you do, because you know, remember this is F4-3, this is from 4 on 3, you know it has to be going this direction. And so the force that's acting, the F3-4 from 3 on 4, F3-4 from 3 on 4, better be equal and opposite to that other one. Okay, and again, you know, so this red line of action better be the same thing as this line here. Okay, through that line of action better be the same angle and everything. Okay, and you know that it's pointing in this, whatever force is at B is pointing in this direction because that's opposite to this force, and you know it's equal. Now at this point you don't know the length of this because you didn't know the length of the other one, right? So but now you know its line of action, you know it's a 3-force member, link 4. Okay, you know the line of action of P, you know the line of action of F3-4, corresponds with that, and you know its direction is that way, you know this one's direction is that way, and you know the magnitude of this, okay? So now you have plenty to solve for everything you need on this member. So first of all, remember, you know that this force, whatever it is, its line of action has to intersect these two. We know the line of action of those, so we know the line of action has to intersect these two and act there. Okay? So you draw that red line. And now you just know the line of action of all three, and you really only know the magnitude and direction of this one. Like I said, you know the direction of that one, but you don't know its magnitude. And you actually don't even need to know its direction. Once you have all that, you can line these all up. Take this guy and you can put it there, and make sure this guy is parallel to it, to this red line. Okay, and draw its magnitude, and make sure this one's parallel to this. Okay, and organize it head to tail, head to tail, head to tail, or sorry, tail to head, tail to head, tail to head, right? And make sure they all add to 0. In other words, make sure they make a loop. And when you do that, you will know the measured length of them all, and their direction, and everything you need to know. Okay, so now you will finally know, with all that rigor, you now know the magnitude, the length of that one, F34, which means going back, you now know the length of these, which means now you know the length of this one, and now you know the length of this one, F23, which means now you also know F32, right, from 3 on 2. So let's draw that one. That's here, okay? So you now know F32 from 3 on 2. Its line of action is along here from A to B. Okay, and you better maintain that. And you know its length and you know its direction because it's opposite the other one on 3. Okay, and you also know this is a 2-force, 1-moment member, because you know there's got to be a force here, a force there, and then there's a moment there. Okay, so that means, so you have everything you need to solve for M1, 2. Right, because you know it's a 2-force, 1-member thing. You know the 2 forces apply there. You know there's some moment. Okay? Sorry, 2-force, 1 moment member. The 2 forces apply there. You know the line of action of this one, which means you know the line of action of this one has to be parallel to it. Okay, so these guys have to be parallel. You know they have to be equal and opposite. So now you know this points in the opposite direction. It's the same length, which you know this now. And now you know that the moment has to be, this distance, which you could measure, times one of these forces, which you know its magnitude, has to resist that. And so it would be that magnitude times that distance is the moment, and you'd have to draw in the right direction, and you could solve it. Okay? So you can see how you can deduce and measure graphically how you use all these principles to solve for the moment. Okay, let's do one more example here on this. Say you have a slider crank mechanism. Let's say all the joints are smooth and everything. There's no friction. Okay, and say you have a point P, a force P that acts at point Q, as you see right there, slightly off from the center of this. Okay, slightly above point B. Okay. So if that load pushes on that fourth link, okay, what is the input moment? What moment would I have to put on 2 to have this be in static equilibrium? Okay, again, it's a static equilibrium thing, therefore you can use this graphical approach and you can deduce stuff to solve for it. Okay, assume, of course, the figure is drawn to scale and that the prism joint is smooth. In fact, assume all the joints are smooth, in other words, friction-free. Okay, well, let's start deducing stuff to solve this. Okay, let's pull out link 3. This link right here, let's just draw it as a skeleton diagram line here, where that's point A, that's point B on both ends. You know there's no moment, there's no force acting on there externally or anything. And so really, there's just a force at A and a force at B, so it's a 2-force member. And they're going to be, their line of action therefore has to be along that, connecting A and B. They have to be equal and opposite. Okay? If you're pushing with P, there's going to be a moment that goes in that direction, and so it's going to be in compression, so you know kind of the direction. So again, you know everything except the length. You can't graphically measure the length of those 2 vectors. F2-3 and F4-3. You just know they're equal and opposite and their line of action. Okay, so now let's look at link 4. Okay, let's draw that. Now, what kind of a body or a member is link 4? Well, we know we have a force acting on it from B. We have a force acting on it at Q, which is given to us P. We have the magnitude, direction, sense, everything of that. And, of course, there's going to be some kind of load from the ground, from the sliding component, the prism joint. And what's that going to be? Well, remember at the beginning of the lecture, I said if you have two bodies that aren't connected to each other and they're touching each other, they can't impart a moment on each other. They can only impart a force. And if there's friction, then that force can be broken into two components, a tangential friction force and a normal force. Okay, but we said this is a smooth joint. They even went out of their way to say the prism joint is smooth, so there's no friction. Therefore, the force from the ground to the link 4 has to be normal to it. Okay, so it has to point, the force from the ground has to point up on it, or point normal to it. It can't have a tangential component because there's no friction. It's a smooth joint. Okay, and it can't impart a moment. So again, two bodies in contact with each other but aren't connected rigidly or anything. They're just two separate bodies in contact with each other that don't have any friction between them, can only impart a force, no moment, and that force has to be normal to the interface. Okay, so from that, this is a 3-force member. There's a force at B, there's a force at Q, and there's some force from the ground that has to be straight up and down. Okay, so from a 3-force member, so first of all, the line of action of this, it's this dotted line of P. Okay, the line of action of the force at B. Okay, it's going to be this same dashed line from A to B, right? Because it's going to be equal, whatever that force is on B is going to be equal and opposite to F4-3. It's going to be F3-4. It's going to be along the same line of action here. And so if you know the line of action of two of the forces, this one and this one, the third force has to intersect, the line of action has to intersect those. Okay? Well, you didn't know the point of application of this normal force, but it's vertical because it's got to be normal. And now it intersects the two, so it's really only got to be this one. Here's the line of action of that one, here's the line of action of this one. This one's got to be normal and it's got to intersect it, so it's got to apply right there, right? Okay, and again, we know the magnitude and sense of this one, and we know the lines of action of all of them, so you can align them. Okay, here's P, it's this one's scaled up, so you can see it, but it would be this length. We're zooming and scaling up, so I don't recommend if you're doing this graphical approach because you want a ruler to get it all right. Okay, and you draw, tail to head, tail to head, tail to head. This one's the F1-4, this one's it has to be with that angle. And because their lines of action, their angles, how they have to be with each other, you can measure how long they would need to be. So the magnitude of all of them, and you'd know their direction. Okay? Okay, so now all these forces. Okay, and this is the key one. Now that you know the magnitude and direction of this one, well, first of all, you already knew the direction was opposite this one, F4-3, F3-4, but now you know the magnitude, which means if you know the magnitude of this, then you know the magnitude of that. If you know the magnitude of that, you know the magnitude of F2-3, which means now if we draw link 2, we know the magnitude of F2-3 has got to be equal to the magnitude of F3-2. From 3 on to 2. And they have to have the same line of action, and they point in opposite directions. So now the force that acts on A, its line of action, its length, direction, everything. Okay? Okay, so now you ask yourself, well, what member is link 2? Well, again, there's a force from O2, there's a force from A, and there's a moment on it. Okay, so it's a 2-force, 1-moment member. And the magnitude and sense and the line of action of this one. Therefore, because it's a 2-force, 1-moment member, and the line of action of this one, the line of action of the one through O2 has to be parallel to it. Okay, and you know it's got to be equal and opposite. So you know the magnitude of that, you know the magnitude of that, you know it's opposite. And so now we're getting really close. You know the distance between the two. You can know that magnitude times that distance is the moment that would be caused by those two forces, and therefore is the moment that need to be resisted by the M12. So the M12 would be of magnitude, 4 inches times whatever that magnitude F12 or F32 is, and you'd know the direction it would need to be. Okay, so you can deduce everything. Okay, so that's a nice exercise to understand what's going on with forces in a mechanism graphically. But really the more rigorous way is the first approach I did, where you draw free body diagrams and just come up with a big ugly matrix and solve for them. Okay? Okay, but now the final point of this topic is dynamic force. Okay? So what about for dynamic scenarios? Okay, what if we have a mechanism and we're loading it externally, but it's also moving with some kind of velocity or acceleration? How do you solve for the internal forces? Because so far everything we've done we can't do if it's dynamic, and the power equation, although it is dynamic from topic 8, or it can accommodate dynamics, it can't find the internal forces. So what if you have a dynamic system, but you want to find the internal forces? Well, you've got to use what I'm about to teach you in this section, okay? Okay, and the key is you have to use Newton-Euler's equations for planar motion of rigid bodies. So this is for planar scenarios, which everything in this course is planar, okay? And the Newton-Euler equations, okay, basically say this, okay? The dynamics of rigid body of mass, m, undergoing planar motion are governed by the following two vector equations, okay? So say you have a potato and you've got a bunch of forces acting on it. It's not shown here, but say there's a bunch of forces acting on it, okay? Well, you sum all those x components together and you sum all the y components together, and according to Newton, all those forces have to equal mass times acceleration. F equals ma, right? Now before, it was all static, and so the acceleration was 0, and so F equaled 0 instead of ma, because the a was 0, right? And so we summed all the x components, we summed all the y components, we set them equal to 0, and that's static. Well, now we sum all the x components, and we sum all the y components, and we set them equal to the mass of the potato times its acceleration, okay? And that's linear acceleration, right? The acceleration along a line, right? The straight line. It's not angular acceleration. So, but the problem is on any given potato or link or member or whatever, the accelerations at different points, the linear accelerations at different points are different. So which acceleration do you use? Well, you use the acceleration at point G, which is shown here, which is always the center of mass. Okay, so basically, if you have a potato and it's accelerating, and you know the acceleration at the center of mass, you times that acceleration by m, and you set that equal to the sum of all the force vectors. And that'll get you two equations, one for x component, one for y component, and now you've dealt with the force issue, okay? And again, it doesn't have to be static. It's some finite acceleration, okay? Okay, but now you've obviously got to sum the moments together, and you've got to take into account all the moments, from the forces, as well as the moments just from the couples and the torques and the moments on it, okay? Well, you do that. On the left side of the equation, you would do all those things. Now remember, where you sum the moments of all the forces on the potato, we proved earlier, doesn't matter if it's static equilibrium and all the forces equal 0. Because the moment's going to be the same no matter where you pick that point, and it's going to be 0 if it's in static equilibrium, right? But now this is dynamic. This is not static, and so where you pick your point matters. So if you pick different, say you pick a point B, okay, it's just some point, whether in the potato or outside the potato, and you use that point and you point from B to the point where all the forces apply on the potato, and you use those and you cross product those with all the forces, that will, and then you sum all the moments into that. That's the left side of this equation, where we took the moments about B here, and we sigma, we added them all together. Well, that left side of the equation would be very different if we picked different points, not B. Say we picked G. Say we picked some weird point, somewhere over here, something like that. And we summoned, we took the vectors, the point from the new point to the point of application, all those forces, cross product them, added all the moments. They would be very different, okay? But whatever the left side is, whatever point you picked, say you pick B, okay, you can make it equal to something that's correct if you use these equations, okay? These Newton-Euler equations, okay? Okay, and so what those say, and it's a little confusing. You might not have learned this equation. You probably learned it for a special case, but the more general equation is shown here. And you have two options. Okay, so if you pick the point B to do all that stuff I told you to calculate the sum of the moments on the left side, then what you could do is you could either take the mass moment of inertia about the center of mass through G. So here's the center of mass through G, the mass moment of inertia about an axis through this point coming out at you, perpendicular, times the alpha, the angular acceleration. You'd have to know the angular acceleration. Okay, and then add it to the mass of the potato times the location vector from B to G. Here they say G slash B, or from B to G. And then cross product it with the acceleration of at the center of mass. That would do it, okay? So that would equal what it would be if you chose B to take all the forces on it, take the moment about all those and add all the moments to it, okay? That would do it, okay? Or you could now, if you didn't want to take the mass moment of inertia about G, you could have the mass moment of inertia about B, the point you picked, coming out at you, okay, coming out like this, of this potato, times it by the angular acceleration, plus the same mass, times the same vector, RGB, pointing from B to G, cross the acceleration of B now. Okay, if this was a point on that body, that would be the acceleration of it, okay? That would work as well, okay? Now note, to jump around with mass moments of inertia, you might recall the parallel axis theorem, okay? If you know the mass moment of inertia through the center of mass of something, okay, but you want to find the mass moment of inertia of that same body not through the center of mass, but about an axis that's parallel to that axis through the center of mass, then you would take the mass moment of inertia that you know through the center of mass, add it to the mass of the body, times by the distance from that new axis to there, squared, and that'll give you the mass moment of inertia about B. Okay, so this equation can hop back and forth between the mass moment of inertia at the center of mass and the mass moment of inertia about a different point that you pick somewhere else. Okay. Now, these equations, these two options are both correct. You can prove they're the same. Okay, using this stuff. They become dramatically simplified for two conditions. If we chose B to be either the mass center G, so say we chose the point to be the center of mass, so now B and G are coincident, okay, then guess what happens is that this vector RGB, okay, goes to 0, and the whole right side goes to 0, and you would have mass moment of inertia G, or which would be B, because they're the synonymous points, times alpha. Okay, and that's probably what you learned in high school physics. They probably told you 4 dynamic scenarios. Pick, when you're going to sum the moments of all the forces on the body, or caused by all the forces on the body, pick the point to be the center of mass, because it'll make your life easy. If you pick the point to be the center of mass and find all the vectors of points from there to where all the forces apply, cross product them with all those forces, add it together, add it to the moments on it, then you can just set it equal to the mass moment of inertia through that center of mass times angular acceleration. That's probably what you learned. Okay, but this is giving you a more general scenario. If you wanted to pick a different point, say there was some mathematical inconvenience to picking the center of mass to take all the moments, and you want to just pick any general point B, you'd use these. Okay, but hopefully you can see that if B and G are coincident, then all these cancel, and it just ends up being this, which is synonymous with IG alpha, okay? But another interesting way you can make the right side of those equations cancel is if the point B you fixed doesn't have an acceleration. Like say it's anchored or fixed down, it's a point on the potato, on the body, where it doesn't have an acceleration. So AB equals 0. Well, if AB equals 0, then this also cancels, and you still have mass moment inertia of B. This one can't be G because they're not synonymous anymore, alpha, okay? That also makes your life easier, okay? So if you're going to take the moments about something that's dynamically moving, again, you can take the moments about any point you want, you know, and unfortunately, depending on which point you take, the left and the right side will be very different. But the good news is you can still get equations that are true, okay? But when you're picking that point, either pick the center of mass or pick a point on the body where the acceleration is 0, and it'll simplify your life a lot, okay? Okay, so let's apply this to our good old example. Say it's the exact same example we did before of a 4-bar, okay, where there's an M4 on it. There's gravity pulling down, and you want to find an M2 that balances it, okay? Or you want to find some M2 that causes everything to move with certain dynamics, okay? Okay, and say, you know, I give you the alphas of all this, you know. Say I give you the, angular acceleration of alpha 2, alpha 3, and alpha 4. And I want to find the M2 that will fight against gravity, fight against M4, and will cause the mechanism to achieve these accelerations. Say you already know what those accelerations are, but you want to find M2, and you also want to find all the internal forces. So you can check if any of the links are going to buckle or yield or something like that, okay? So what you do is, for this dynamic scenario, you do the same thing. You draw the free body diagram. You've already done this on link 2. Okay, it's the same forces at the 2 pin joints, same moment 2, the forces are all the same. And the sum of the forces are the same, except the difference is now you times, instead of setting it equal to 0, because it was in static equilibrium, now you set it equal to the mass of the body times the acceleration of point G, the center of mass, in the x direction, because these are the x component. And then you do the same thing for the y component. Again, these will always be the same as the last example, except instead of 0, this is now mass times the acceleration of the center of mass in the y direction. Okay, and then again, we could take the moment still about any point we want, and we can still come up with a true equation. Of course, each equation, both sides of the equation will be very different in this case. They won't always equal 0. But if we could choose whatever point we want, say we chose that point, like we did in the last case, and we got the exact same thing we got from last time. You can go back and look, except instead of equaling 0, we have to use those equations. And again, we didn't choose the center of mass. The point we chose was like, our old B. In this case, it's called O, but it's certainly not the center of mass. So what you have to do is take the moment of inertia of this beam about point O, times it by alpha 2, which they would need to give you, okay? And then it would normally be plus all the other good stuff, right? You'd have to add the vector that points from there to the center of mass, okay, times the mass, and cross product it from the acceleration at that point, times the acceleration of that point. Right, actually, I don't want to confuse you. So since we took the moment of all this stuff about O, let's go back and look. It's like we did it about this, where B is now O. You take all this stuff, mass times the vector that points from that point to the center of mass, cross the acceleration of B. Okay, but the reason this didn't have that term is because guess what the acceleration of that point is? It's 0. It's not moving. It's fixed there. Okay, so it saved us. We would have had to add the vector from there to there, cross the acceleration of that point times m, right? But the acceleration there is 0, so that goes away, and all you have to do is that. Okay? Now again, we could have picked this point to do that, and we could have summed all the forces. The moment from this one would be 0, but the moment